Hello everyone, my name is Edgar Buchanan and I'm a research associate working here in the University of York. My research is about evolutionary robotics, but before that I did my PhD in swarm robotics. And today I'll be talking about swarm robotics. And I think it's good to start with this quote, which says, "Ants are good citizens. They place group interests first." And later on in this same lecture, we are gonna see why this quote is relevant. Before going too much into the details about what swarm robotics is, I would like to mention some of the applications where swarm robotics can be applied, and then we can start seeing how this can be used. A common application is when there is an earthquake or there is any natural disaster, buildings collapse and people get trapped. To rescue those people, it's easy to send other people to rescue them. But something that we need to think about is that when you're removing all these pieces of debris, sometimes they can be really heavy for a single person to handle. So what if we have multiple persons doing this? And about item transportation, we can see some examples in biology as well. For example, ants can carry heavy loads when they are working together, or bees can transport by exchanging the nectar within each other. A second application, again, is about search and rescue. This, for now, we send animals or people to track the people that we want to rescue. But again, people can be heavy and it's easy to transport them to a safe place. And ants can do it in a very efficient way where multiple ants work together and they can transport that. So also these kind of environments are dangerous for any people or animals to go there. There are pipes of gas that they're broken, so it's better to send robots in this case to prevent any further losses. The last one, and really important, is that, for example, when there is oil spillage in the ocean, we want to contain it as quickly as possible because we don't want to other sea animals be affected by this black oil. And we can implement algorithms to achieve this. And this can be done with swarm robotics. So, from biology to robotics, swarm robotics. This lecture is gonna be divided into three main parts. In the first part, we're gonna define the concept of swarm robotics, and we're gonna see one concept that an author proposed, and we're gonna deconstruct it. In the second part, we're gonna talk a little bit more about the history of swarm robotics, that it came from a concept called swarm intelligence. And finally, we are gonna see some examples of applications of swarm robotics where inspiration was taken directly from biology. Without any further ado, let's start with what is swarm robotics. If I had to describe swarm robotics in a nutshell, I will define it as a group of robots working together to achieve a task. And that they need to be decentralized. Swarm robotics is directly inspired of biology, from concept of like colonies of bees or swarm of ants, because these biological systems are very efficient. They can, as a colony, they can achieve great things because they are working together as a team to for the greater good. And we can achieve something similar if we do it in robotics. What if instead of having one big robot that does everything, we have multiple smaller and cheaper ones that they can do it? If one of the robots breaks, we have other robots that are going to replace it. And this is why swarm robotics is important. But let's check one of the concepts in literature. This concept says, swarm robotics is the study of how large number of relatively simple physical embodied agents can be designed such that a desired collective behavior emerges from local interactions among agents and between the agents and the environment. But this is very difficult to grasp at the beginning. Let's deconstruct this paragraph into smaller bits. Let's start with the first sentence. Large numbers of embodied agents. So, swarm robotics is about having large number of robots working together and be embodied. This is really important. We need a physical robot that does something. Otherwise, that will be swarm intelligence that can be designed such as that desired collective behavior emerges. Emergence is really important. We can see emergent behaviors in many places, but one of the easiest ways to find it is when the birds start flocking in the sky. Here's one example of it. Here, the birds are creating patterns in the sky. And they are doing it very efficiently. They are avoiding each other, and there is no like central leader, central bird telling what to do. This emerges just from the interactions of the birds. What are those interactions? Well, they are trying to avoid each other, but at the same time try to beat together each other. They are trying to move towards the same direction. With these simple rules, birds can create these complex patterns in the sky. So we are looking for that in swarm robotics. Some simple interactions between robots that can create an emergent behavior, and we don't have to design that emergent behavior. Here's another example that I like. Probably you have seen it, but it's very impressive how the emergence happens in this video, and I'm gonna play it. As you can see, just by simple action, like standing up and raising your arms, you can create this what is referred as an execute wave, where multiple thousands of people start doing the same thing. I just love it. It's incredible how a small group of people can create these massive emergent behaviors. And the last part, and we have been mentioning this for a while, is from local interactions among agents, between the agents and the environment. Here the key word is local interactions. What do I mean by this? That this interaction should be between the robots and not by an external source to the robots. What we want is to have a decentralized system, because as we've seen in biology, although you can argue that colonies have their queens, yeah, they have their queens, but the queen does not allocate tasks to each individual or to each ant. Each ant knows what to do. For example, the ant is going to protect the colony it's been attacked, or the same ant could be a forager if everything is calm. But why is decentralization is important, and why do we want it in our group of robots? Let's have a look at the next example. Imagine that you have a central computer that sends signals to each robot in your swarm. Each robot will do whatever it's asked to do. But if the central computer fails, the robots are going to be lost. They won't know what to do. And this is a problem of centralized systems. There is a single point of failure. Whereas if you have a decentralized system, if one robot fails, nothing happens, because the other robots can coordinate to cope with this failure. Alright, so 3 characteristics. We want embodied agents, we want physical robots that can do emergent behaviors from local interactions between each other, or in other words, they are decentralized. Some robotics has 3 properties as well, and we're going to discuss them now, which is flexibility, robustness, and scalability. And let's start with flexibility. By flexibility, I mean that if a robot starts at home and wants to retrieve an object, it will try to find the shortest path. If the path is obstructed by an obstacle, then the robot is going to adapt and it's going to find another way to retrieve the object. This is flexibility, when the group of robots can adapt to changes to the environment. The second property is our flexibility. This means that you can add and remove robots at any time, and the functionality of your task is not going to be affected. The performance might increase or decrease, but the functionality won't. And this is because the robots can coordinate to achieve the task. And the third one is robustness. For example, here's a video of a robot moving together to reach the target on the right hand side. They feel attracted to an IR beacon. In this example, 2 robots fail, but the non-faulty robots ignore those robots and they reach the target. This means that since you have a high redundancy, or you have many copies of the robots, if 1 or 2 break down, this will not affect the functionality of the swarm. But the question is this always the case? Is the swarm always robust? And the answer is no. Here's an example of the same task with the same number of faulty robots, but with a completely different outcome. As you can see, it's taking longer for the robots to reach the target because they feel attracted to the faulty robots and they are hard to ignore, which makes the task to take longer to do. Until finally they break apart and they reach the target. But instead of leaving two faulty robots behind, now 4 robots are left behind. Right, we know what swarm robotics is, we have seen the characteristics and the properties. Let's check a little bit of history and see where swarm robotics comes from. And it comes from a concept called swarm intelligence. Swarm intelligence was introduced in the early 90s, and it was basically about the same stuff with swarm robotics, but instead of having physical robots, they are virtual agents. Researchers were studying how emergent behaviors of simulated agents and how they can create different patterns from the local interactions. This is a classic algorithm using swarm intelligence, and what they were trying to do is to achieve the flocking of birds, but this time with virtual agents. And what they did is create the 3 simple rules of trying to stay together but not too close and face the same direction. And from chaos, where all the agents were moving everywhere, slowly over time these agents started to create the flocking pattern that we have seen before. As you can see, the birds are starting to group together and moving towards the same direction in smaller groups. And these groups are going to merge, and eventually there is going to be a single group of birds or virtual agents moving towards the same direction. We've been talking a lot about ants and how they are a strong source of inspiration for some robotics, but even how ants explore the environments leaving trails of pheromone, this was implemented in swarm intelligence as well. Ants, what they do is when they found food, they take it to the nest, but they leave a trail of pheromone. It's like a strong smell. So if other ants find it, they can find a source of food. And here there is another example how this pheromone can be implemented virtually, and the ants feel attracted to it and they can find a source of food and they can finish it eating it, and they can do it in a quicker way. But what if we give a real application of this? Well, people have done it. So, an application of artificial pheromone is in this famous problem in computer science, where a salesman person has to visit all the cities in the shortest time possible, without visiting one city more than once. So what we can do is use our artificial pheromone. We deploy many agents, and all the agents have to visit all the cities, and they are going to leave a trail of pheromone. So without going to any details, the pheromone is going to accumulate where the ants take less time to do all the cities, and eventually it's gonna converge to a solution, which is the solution that we want. So by accumulating the artificial pheromone, we can find the shortest route. One day, researchers said, okay, it's fun to have these agents working in virtual, but what if we make the robots physical? What if we have the same properties but with physical robots? That's when swarm robotics was born. And in this last part of the lecture, I would like to focus on the specific applications where scientists took directly inspiration from biology and implemented it into swarm robotics. So, yes, swarm robotics is the agents with a body. It's an embodied experiment. So you have hardware to run the experiments with. In this first example, it's taken from the fireflies in nature. Basically, how fireflies flash in the middle of the night is they flash because the males want to attract the females. But imagine that yourself are a firefly in the middle of the forest in the middle of the night. If you flash by yourself, you're most likely no one is gonna see you. But if you flash at the same time as your other fireflies, this quantity of light is gonna increase, and the likelihood of female fireflies to see you is gonna increase. So fireflies need to synchronize so this light is bigger and they can attract more females. So what if we do something similar with, instead of using fireflies, we use robots? Let's have a look at the following example. In this example, the robots work very similar to the fireflies. They have a ring of LEDs and they flash light at different time intervals with the aim of synchronizing. Here in the video we can see how the robots synchronize over time. Because they have cameras, they can see the light from other robots and they can have a slightly smaller delay in the time where the light starts until all the lights are synchronized with your neighbors. So it's by changing these delays. Here's an example of two robots synchronizing. And now they are gonna test how scalable is this? How many robots can you synchronize at the same time? As you can see, the robots are very well, can synchronize easily regardless of the number of robots. But the question that you might ask, how can this flashing be used? Well, you can use it as a heartbeat, and one robot that stops flashing, that means that that robot is broken and you can fix that robot. So it's a very safe way to detect faults in other robots. In this case, one robot is fixing a second robot. And yeah, this can be really useful if you want to detect faults and repair those faults. Let's have us look at another example. Again, I'm back with ants, and now we are gonna use their pheromone. But the problem here is that ants use a physical pheromone, which is a chemical that they leave behind to attract other ants and in order to find a food source. The problem with physical pheromone when you want to deploy it with robots are three main issues. If you use physical pheromone, you have to clean every time that you run an experiment, and that can take time. If you use a chemical as a pheromone, that's gonna be expensive because after each run the robots have to leave more new pheromone. And the third one is that it's not very eco-friendly because the chemicals that you're using might pollute water or the air itself. So instead, the authors have used virtual pheromone. And let's see one example. In this example, there is the home base, which is in the bottom left, and there is the food source in the top right corner of the screen. How the robots find the food source and the home area? Well, it works by using virtual pheromone, which is just communication between one robot and another. So basically, one robot finds the food source. This robot starts sending a signal to the other robots and saying, "Oh, I found the food source and I was the first to find it." A second robot is going to receive the message and he's going to say, "Oh, this neighbor found the food source and I'm the second one to find it. I'm going to send this message to a third one." And so on and so on. So if I'm a robot that I'm lost and I want to find the food source, I just need to follow the neighbors that have the lowest counter, because this means that these robots are the closest to the food source. And if I want to get to the home base, I do exactly the same. And in this way, you can have these emergent chain formations using virtual pheromone, where you can have a continuous collection of food. And this is very scalable. For example, as you can see in the video, there is a person removing and removing robots, and the collection keeps going. Although, there's gonna be a point where it breaks down and it doesn't work anymore. And it stops working when there are not enough robots to create the chain. Therefore, they get lost easily. So, the key point here is to identify the lowest number of robots to create this chain. Also, another issue with this is that you have to be careful of not having too many robots, because if you have too many, they're gonna spend more time avoiding each other rather than collecting food. And now we have 5 robots in the arena, and we're gonna see that the robots are starting to have problems. There's one robot that is completely lost in the top right corner, and so on. So the limit here is around 4 and 5 robots to create this chain of collection. And the interesting thing is that as soon as the person starts putting robots again, the chain formation happens again. And there is no leader coordinating this. The robots are doing that by themselves. And now the same person changed the position of the nest, and as we saw, as I was explaining early in the lecture, some robotics is very flexible. They're gonna adapt to the changes in the environment. And yeah, this is very interesting because over time, instead of having this curve, again they are moving slightly to create a straight line between the food source and the home, which is the shortest path. So they are optimizing the trajectory. And just by following the neighbor closest to the target. And the final position, and this is perhaps is the most interesting one, is gonna be very crowded, and most likely it's gonna cause the robots to avoid each other a lot. So yeah, this is the chain formation, a very good example of how some robotics can be applied and of the properties of some robotics, that they're scalable, flexible, and robust. So yeah, let's have a look at the final example. This last example ants recover an object that is way heavier for a single ant to do it, and they coordinate and they just pull the target all together, distributing the weight across all the ants. This is usually referred as division of labor. And we could do something similar, as I was mentioning in the introduction, when we are doing search and rescue. Maybe a robot is not strong enough to carry a person, but what about multiple people? Sorry, what about multiple robots transporting a single person? And let's have a look. In this case, there is a person who fainted, and the objective of the robots is to rescue this person. So what they do is they come close to the target, in this case the person, and they grip. Then they change color. When the robots change color, it means that they are ready to pull the target. And other robots are gonna approach the robots and are gonna grip the robot as well. After we have enough number of robots, then the robots can move the target of the person and follow a beacon that might be in the home area where it's safe. And let's see if this group of robots can handle the task and they can achieve it. Now the robots are ready to transport the person. And hooray! The robots can do it. They can transport the person. And right, that's all for me. Let's recap very quickly. Swarm robotics is a group of embodied agents that through emergent behaviors, through local interactions, can solve a task or they can produce a behavior. There are three main characteristics. They are decentralized, they produce emergent behaviors, and they have a central task, a common task. They have three properties. The first one is it's flexible. If the environment changes, the swarm is going to adapt to those changes. They are scalable. We can add and remove robots at any given time, and the functionality won't be affected. And finally, for the most part, they are robust, which means that if one robot breaks down, it doesn't matter because we have another group of robots that they can replace it immediately. Then we saw a little bit of history of swarm intelligence, that it was all about agents, simulated agents, and how we transition from these simulations to real hardware to run with physical robots or experiments. And yeah, that's all. Thank you very much. This is a bridge made with ants, for ants, and thanks. If you have any questions, please feel free to email me those questions and I can answer them. I have some very interesting videos here. You can, all the videos that I showed here, you can find them here in the literature, in the reading material. And also I have included some blog posts where you can find more information, more videos, and more. And that will be me. Thanks.